This is Learning Assessment Problem 9.8. The problem-solving strategy to be applied here is that of maximum average power transfer. We have a network with an arbitrary load impedance Z sub L connected, and we are asked to determine the value of that load impedance to achieve maximum power transfer into it and the value of that maximum transferred power. We'll label some items on this circuit diagram. The nodes to which the load impedance is connected will be A and B. The voltage across this inductor we'll call V sub L. And ultimately we're going to determine the open circuit voltage appearing across the terminals A, B when we've removed the load. The condition for maximum power transfer is achieved when the load impedance Z sub L for maximum power transfer is equal to the complex conjugate of the Thevenin impedance of the network looking back from the terminals A, B. So our first step will be to find the value of the Thevenin impedance, ZTH. We'll determine this Thevenin impedance by setting the two voltage sources to 0 and analyzing the resulting passive impedance network seen at the terminals A, B. This is the equivalent circuit, and we'll determine the Thevenin impedance looking into the terminals A, B. We'll call this series impedance combination Z1. Then Z1 equals 2 minus J2 ohms, or Z1 equals 2 square root of 2 at an angle of minus 45 degrees ohms. Then we can calculate the Thevenin impedance as the parallel combination of Z1 and the J2 ohm inductor. So Z Thevenin will equal, which is equal to 2 square root of 2 at an angle of plus 45 degrees ohms, which in rectangular format is equal to 2 plus J2 ohms. And from our matching condition for achieving maximum power transfer, we'll have that ZL maximum power is equal to Z Thevenin conjugate, which is equal to 2 minus J2 ohms. The Thevenin resistance component then is equal to 2 ohms. Now we're ready for the second step, which is to find the maximum power transferred to that matched load. This is equal to the magnitude squared of the open circuit voltage, or the Thevenin voltage, divided by 8 times the Thevenin resistance. And recall that we said the Thevenin resistance was equal to 2 ohms in this case. So we have to determine the voltage VOC by removing the load. We'll begin by using voltage division to determine the voltage across the inductor in the circuit V sub L. So we'll have that V sub L is equal to the 24 volt source times the impedance of the inductor divided by the total series impedance in that circuit. And this is equal to 24 at an angle of 90 degrees volts. Then the open circuit voltage is equal to this V sub L plus the 12 volt source, 12 at an angle of 0 degrees volts. This is equal to 24 at an angle of 90 degrees plus 12 at an angle of 0 degrees volts, or VOC is equal to 26.833 at an angle of 63.43 degrees volts. Now we're ready to calculate that maximum power which can be delivered to that matched load as 26.833 volts squared divided by 8 times the 2 ohm Thevenin resistance. And this is equal to 45 watts.